So we move on to level 3. Level 3 statistics. In the continuing mission to do all of this year's exams. So this is level 3, apply probability concepts in solving problems from this year. So I'm going to be using the formula which are given to you, and also the most common calculator, which is also used by New Zealand students. So that said, let's do it to it. So for this, we're told that a school sport New Zealand organises secondary school, blah, 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 okay, since 2000, okay, great, good for him. By sport region and gender, okay, the most recent 2023 sports census, 91 different sports. I haven't seen these questions before, so I'm just going to underline what I think maybe relevance. Total of 1,44862. Yeah, that's going to come into importance. So question 1, at least one sport. So they can go in more than one sport. So the school census showed that many played badminton, table tennis, and hockey. Okay. So it's arguable that they're all sports, but let's go along with it. Follow-up surveys in some regions has an estimate who played a combination of sports, badminton and table tennis and hockey. Oh, okay, so it's all three. So they pretty much really imply that they want you to use a Venn diagram. So let's do that. So let's say that's badminton. Oh, it's terrible. Circle. Badminton, table tennis. So we have this kind of Led Zeppelin symbol here. So let's start off with these for all of them. So there are 500 who play all three. So let's call this one badminton. Let's call this one hockey. And let's call this one table tennis. All right. So badminton and table tennis is 800. So I'm going to presume they mean badminton and table tennis, ignoring hockey, which means that there must be 300 who play badminton and table tennis. So that'll be more than that. Okay. And then badminton and hockey is 1100. So that means this must be 600. Doesn't it? Badminton. 11, yeah, 600 plus 500 is 1100. Table tennis and hockey is 600. So there must be 100 students there who play only hockey and tennis, but not badminton. That's interesting. So now we can make out these other three. So there are, let's look at hockey. So 13,304 minus 100 minus 500 minus 600. 12,104. And now let's do badminton. Fast forward if you want. So 11,195 minus 600 minus 500 minus 300. That's really rounded numbers. But let's take those with a grain of salt. 9795 And lastly, we can table tennis. Table tennis, there are 2125. Would be more than that. Minus 300, minus 500, minus 100, 1225. Okay. I don't think they're going to give us any marks for that, but I think you need to be able to do that to solve it. So estimate the probability that a randomly selected student, so this is going to be a participates in only one of these sports. Okay, so probability only one. So it's always going to be something out of something, and it's going to be that big number, that 144 number, 144862. Now, how many play only those sports and no other sports? So 97 5 plus 2104 plus 1225 is 23124. All right. So now we have the numerator, denominator. Now we can divide it by 1, 4, 8, 6, 2. Is this number here? So I'm going to do a hard and fast rule for this exam. I'm going to go 4DP every video. So 1596. They don't want it in percentages, do they? No, they just want it, they just want it as a okay. Very good. Let's move that. The student is randomly selected from those who play hockey. Okay, so that's our denominator. Probability they play both hockey and table tennis, but not badminton. So here we want probability they play hockey and table tennis, but not badminton, given that they play hockey. So it's out of the players play hockey, so how many play hockey? 13304. Now, how many make that criteria? So hockey and table tennis, but not badminton. Hockey and table tennis, but not badminton. So 100. That's interesting. Yep, okay. Makes sense. 100 divided by 133. What? Ooh, really tiny. So, so that's 7.1, 7.516. One six times 10 to the negative 3, which is 0.007516. Yeah, really, really small. Seems really, really, really small. But yeah, that's correct. Okay, fair enough. Go with it. Interpret the relationship between the events student plays badminton, student plays hockey. How do your answer explain these two events, whether these two events are independent? use calculations and statistical reasoning to support yourself. Okay, so here we have a couple of things that we really need to go over. Gonna watch one piece of the video. Really watch this one. When they say independent, they want the statistical definition of independent. They don't want you to do anything like, badminton New Zealand as independent from hockey New Zealand. Don't do that. I have actually seen students do that, try to sort of talk their way into marks. You will not do it. You need to know the definition of independent. Confusing that a bit more is two things. First off, they do not give you the formula for that information. You need to know that. Secondly, a lot of students mix up independent with mutually exclusive. They're not the same thing. Independent means that one happening does not affect the probability of the other one happening. There's two ways of working about it. I'm only going to use one way. There's one using conditional probability, but there is a hard, fast definition that I'm going to use for this one. Mutually exclusive means that if one happens, the other one cannot happen. So we're only looking for independence in this case. So I'm going to give you the definition of independent. If two events are independent, and I'm going to call these event A and event B, then the probability of A and B happening, which can happen if they're independent, is going to be the same as the probability A happens times probability B happens. If there's no conditional, so probability of A given B is going to be the same as probability of B given A. If they're independent. But we're not going to use that definition. It gets us into trouble, I think. We're going to use this definition. All right, so in this case, they're independent. The probability that they play hockey and badminton equals the probability of hockey, if we ignore everything else, times the probability that they play badminton. If they're independent, if one doesn't affect the other, then these probabilities will not change. Okay, we need to work out what these are. So, what is it going to be over? It's going to be over that big number. It's just the probability of all students. There's no condition here. So it's going to be that big, huge number. 144,862. All of these are going to be over this number here. So the probability that they play both. And I can use this one here. So how many play both? It says now in the question, isn't it? It's badminton and hockey, 1,100. So that's 1,100 over that huge number, and we're going to have a really, really tiny number again. So 1100 divided by 144,862. So another really, really, really tiny number. I hope these things can go. Let's convert that into just 0, 0, 7, say 76, all decimal places. All right. Now we need to know the probability that they play hockey. Ignoring everything else. So probability they play hockey we're just going to ignore. So how many play hockey? It's 13,304. 13,304. Would have thought it'd be more than that. Okay, 144,862. Grab our calculator again. 3384 divided by 144,862. That number there. So I'm going to go that 4 decimal places again. So 0.0918. And now we need the probability that a randomly selected student plays badminton at all the students in the survey. So it's going to be something over that 144,862 business. How many played badminton? 11195. So 11195. Divided by 144,862. And 0.773. 0.0773. Sorry. Okay. Now we can do the maths, the sort of insight. So probability that they play both is this number here. So a question we want to say is, does 0.0076, does that equal what we've got here? And we can multiply those two together. Clear that. So 0.0918 times 0.0773. Do we get same number there? Ooh, we get pretty close. Don't we? We get pretty close. We get it. 0.0796. Now, have a bit of a problem here. So now it depends how you define close or close enough. So the answer would be they're almost independent. But not quite. Okay. Here is really tiny. Wait a second. Let me see. Yes, I missed this place there. 0.7. Okay. And it's so close. I mean, it's for all intents and purposes, they are independent, but there's a really, really, really small conditional. There is a tiny conditional probability. Really, really small. And in fact, for statistical purposes, it's virtually zero. So you could actually answer it kind of either way in this question. You kind of could fudge it a little bit, but as long as you get these numbers, I think you're going to be okay. As long as you say they're pretty close. But they're not exactly independent. We're going to say the close-ended counts and horseshoes and hand grenades. Now we're told that a school is comparing the risk of football injuries on two different playing surfaces, artificial turf and natural grass over the season. Data from football matches played at this school showed 30% of games were played on artificial turf. The rest of the games are played on natural turf, so that's going to be 0.2. They're mutually exclusive. On artificial turf, the probability of the player getting hurt is that. Probability of injury, given that they're on grass, is that. All right. So, given that a player was injured, calculate the probability that the game was played on turf. I like how you can make this one. Let's work these probabilities. Okay, so the probability they're on turf is 0.8. Probability that they're on grass is 0.2 for all games. Fair enough. Probability getting injured was 0.4. So probability of injured, given they're on turf, is 0.04. Probability of getting injured, given that they're on grass, is 0.1. I would have thought they would have been higher on artificial turf than grass. So, we kind of want the branches, don't we? So let's do a probability tree. So this is artificial turf. This is grass. So this is 0.8, 0.2. This is just sort of visualize it. And this is injured. And this is not injured. Injured. Not injured. So injured is 0.04, 0.96, 0.1, and 0.9. Okay. Let's complete this tree because I think we're going to need to do this. So 0.8 times 0.04, 0.032. Z is 2. And 0.8 times 0.6, 0.768. Right, and this is going to be 0.02, and this is going to be 0.18, I think. 2 times 0.18. Okay, so given we've got that, what is the probability that the game was played on artificial turf? We could kind of reverse engineer it from here. We could kind of like say, okay, so there's 1,000 people played, times this by 1,000, times this by 1,000, divided by 1,000. and then we can work that out from there. That's a kind of a rough shot way, so I'm going to kind of do the algebra. Actually, I'll do both ways and see how they work. So here, let's say let's multiply this on by 1,000. Oh well. So it's going to be 0.032 plus. So this is the probability that they're injured. 0.02. So the probability that they're injured out of all the students is going to be 0.52. So yes. 0.05. This is 0 there. Okay. 0.052. And it's good injured. What is the probability that they played on artificial turf? So the probability that they played on artificial turf, given that they were injured, is going to be 0.032 over 0.052. That's going to give us the answer. So 0.032 divided by 0.052 is 0.6154. Okay, that's one way we could do of doing this. This would be kind of like the brute force way of doing it by intuition. Let's do it though using Bayes' formula. So probability that someone is injured is, we've already worked it out, and it's going to be 0.052. So now we want to calculate probability that they're on turf, given the fact that they were injured, which is what we try to work out, is going to be probability they're on turf and injured divided by the probability that they were injured. Okay, so that's going to be 0.032 divided by 0.052, which is what we had before. And it's going to be 0.6154. So here's kind of like the algebraic way of doing it. And this is kind of the intuitive way of doing it. Another way of doing it is to multiply it through by, say, some big number and get the actual numbers. But you'll get the same answer anyway. Now we have a question that's real statistics, really. The school claims that in general, students playing football, more injuries occur on artificial turf than on natural grass. Discuss why we should take care using this data to make this claim. This is a really, really good question. So we want to look at the relative risk versus the frequency. The frequency, so what did we make out? So 0.032 of 0.052 0.052, which is 61 point, what did we say it was, 54%. That's right, yeah. Of those who had injuries had them on artificial tube. Okay, so and that's true. So in total numbers, most of the injuries do occur on artificial tube, but the relative risk, probability that you get injured, given that you're on grass, is 0.1, and the probability that you get injured, given the fact that you're on turf, is what was it, 0.04, right? That's what, 2.5 times more likely to get injured. So there is a problem there because 80% of the games, the vast majority of games, are on turfs. Now, what else could be wrong here? Well, let's talk about things that maybe, if you're kind of really analysing this deeply, we could say that this is only for 1 year, okay, and maybe like there was something wrong with the grass. So there may be some other variable going on. So we would want it over multiple years. So maybe that year there was a lot of rain, so it was really slippy because you don't slip so much on artificial turf. Okay, that's one thing. There may be like what's called a lurking variable as well. And that is maybe the different teams would play on, say, different surfaces. What I mean by that is that if you were in the first 11, your probability of getting injured is greater than if you're in, say, the third 11 social team. Okay, but the first 11 will play on the best field, whereas the third 11 will play on a different field. And the first 11, because the tackles are going to be more meaningful, they're going to be faster games. They're going to, by definition, than the social teams. If you're playing the third 11, you're not going to slide into a tackle and take a guy's knee out, something like that. So then there may be some lurking variables. But the big thing is that the vast majority of these games have been played on turf. So the last part of question 1 is kind of an interesting question. So let's say estimate the probability from a group of 3 randomly selected football players. Only one is injured during this game. State and justify your assumptions that you have made in calculating this probability. Interesting way they put this here, because there's 3 different ways of answering this question. So I'm going to go over one. So method 1, the assumption is that it's random from different games. okay, which isn't really stated there. It doesn't say whether these are all on the same game or not. So for this one, we can use the probability just of being injured, full stop, regardless of what turf they're on. So the probability that they get injured, we worked it out as 0.052. Remember that we worked that out in the last question. Okay, what sort of probability we got now? We have now a binomial probability. You could work this out, I guess, theoretically, using probability trees. In fact, I know you probably could, because binomial comes from probability trees. But it would just be really time consuming. It would be a real pain in the neck. So I'm going to just use binomial theorem. We've got a shortcut. Let's at least use it. It's going to be binomial. The probability is of the event that we want, and it's going to be 0.052. The X that we're looking for is 1, and there are 3 trials. Okay, so now we grab our calculator and do it. Now, in the case of calculators, if you have a later model, there is a mode right down the bottom of the menus, sort of way down here, where they do the probability, and it does it really, really well. But this emulator doesn't have that, and I'm just going to use this so you can see the mechanics of what's going on. So I'm going to go to stat mode, distribution, binomial distribution, and I want binomial for a single point rather than cumulative. So it's that there, and I don't want list, I want variable, and it's got all the information we want there. So the probability is variable. Okay, can't do net arrows. 0. The number that we're looking for is 1. The number of trials is 3. And the probability that you're injured per trial is 0.052. And it's going to be 0.142. The X equals 1 is 0.14. This is telling me that my washing is done. It's always good to know. So it's 0.1402 if we assume that these are from different games. Let's kind of do it. Let's assume that it's on artificial turf. So this one, the probability that you're injured, given that it's on turf, is 0.04, and it's going to be exactly the same X and N, so let's grab a calculator with that. The other thing that's changed is the probability, and it's going to equal 0.1106. So the assumption here is it's on turf. Third assumption, if we say it's on grass, so we choose a game which is on grass, and it's going to be selected again, so the probability is going to change. And again, the only thing that's going to change here is that and 26.14. Okay. You could do what's called no, in fact, I'm not going to do that. You could do what's called a weighted probability, but no, I'm just going to leave it like that. You'll do that at university. It probably makes a little bit more sense if I add 80%. But yeah, let's do that. Let's do that. So 0.8 times 0.1106 plus 0.2 times 0.2614, 13.132, 0.1313. You would get sort of any extra marks for that, but that's another kind of option that you have that this selects. All right, question 2. In the same survey, 26,950 played netball, 26,572 played basketball, 6,000 played both netball and basketball. If a student is selected random and is known to play basketball, what is the probability that they play basketball, play netball as well? So let's do a Venn diagram. So let's call this one netball. Let's call this one basketball. And we know that 6,000 play both. That sounds about right, because a lot of those netball players in the silver ferns also play basketball. Similar games that you score points by putting balls through a hoop. It's up in the air. If we have netball, so how many are on this side? So this is going to be pretty easy to work out. So 20,950, and this is going to be 20,572. Okay. Give what? I don't know if we need to do that, but I'll do it anyway. So then no one's played basketball, so it's going to be out of that 26,572. How many play netball as well? So 6,000. Both given basketball as this. So we grab Mr. Casio, 6,000, 2657. So 0.2258. Just ask for a percentage. No, just have it like that. Okay, give one reason why this may be only an approximation. It is estimated, so it says specifically that 6,000 play both netball and basketball. Who's making this claim? What do they base it on? It seems like a really, really rounded number compared to this exact number here, 26,572. 6,000 seems really ballpark. It is, to use X mark statistic. It's kind of a statistic that just falls from the heavens. It comes down from the hand of God. But it's the only number we've got, and they wanted us to do it, so let's use it. Right. Explain whether the events student plays netball and student plays basketball are mutually exclusive. Well, because netball and basketball is not the empty set. Okay. The number of people that meet that criteria and basketball equals 6,000. 6,000, if I'm going to shatter any mathematical problems here, does not equal 0. If they were mutually exclusive, you'd have the numbers that do basketball here and the numbers that do netball here, never the twain shall meet. So they're mutually exclusive. They're not the only options, of course, because there are other sports, but for us, there is an overlap, so they cannot be mutually exclusive. Now we're told that concussion is a common concern, especially head knocks in contact sports. Okay, great. True. Given a positive or negative result for potential concussion, and they are not always accurate. So, study 298 secondary school students, rugby players, had head knock injuries. After the game, the sideline test was used. Medical assessment was done whether each player had a concussion or not. Table below. Okay. So these people had a concussion, did not have a concussion. Positive test, negative test. So let's kind of go through it. So it's worth going through it. So these people had a positive sideline test and they had a concussion, right? So that is a true positive test. They had it and they tested positive. This one here, they had a concussion, but they still tested negative. That is a real concern. That is like twice as big as this. So if you have concussion, you're twice as likely to get the okay than if you didn't, than if you failed that test. You failed this test, meaning you had concussion. That's a real problem. That says that this test that they're doing is not only really, really poor, it's actually quite dangerous. It's really dangerous. If somebody has concussion, you don't want to send them back on the field to get injured even more. That's really dangerous. So that would be setting off alarms if you are looking at that. I don't know whether this is going to be tested, but it's a kind of a problem. So this is a false negative. So they did not have a concussion, but they still tested positive. Maybe they just need accident, but they didn't have concussion, but they gave the symptoms of having a concussion. And I mean, that's still twice as big as this. So this is a false positive. And this is a true negative. So these are people who didn't have concussion and they tested negative. So that's a concern. But let's get on with it. Let's get on with the stats. Okay. Calculate the probability that a randomly chosen rugby player had a concussion or had a positive sideline test. Well, probably to have a concussion is going to be 0.0474 plus 0.131, or that they had a positive test plus that. Share this with you. So 0.074 plus 0.131 plus 0.124, 0.329. Okay, so these people should not have gone back onto the field. If you are showing the signs of concussion, even though you test negative, probably better safe than sorry. So almost a third shouldn't have gone back onto the field. We could have gone one minus that to find that number. Okay. So the safety guideline states that most head knocks in school rugby do not result in concussion. Does the data from the study support this claim? Now, there is a couple of things that need to be said about this. Notice the wording here. Who experienced a head knock during games had concussion. So it's technically true, but it does sort of open a kind of a bias window. What if they didn't have a head knock that they noticed, but still had concussion? There is a phenomenon called delayed concussion, which you don't show symptoms or head knock during the game, but you still have a technical concussion. So that's just silent, but we'll ignore that for now. Does the data support this claim? So we're just going to look at the data. So of the number proportion who did not have concussion is going to be those two combined. So 0.124 plus 0.671 is greater than 0.5. So most of the time they're not going to have concussion. Is that so? 70.795. So if you would say all of those tested, and that's a little caveat there, 79.5% did not have concussion. Therefore, the claim is true. Well, valid. Okay. Now we're given a claim by a coach that if a player gets a positive sideline test, there's a 1 in 4 chance that they have a concussion. As the data on the study support the claim? Well, okay, what we're really saying is we want to work out the probability that they have a concussion, given the fact they have a positive test. That's what they're really asking for. And we want to test, is that equal to 0.25? So it's sort of a test. Well, let's work it out. So the probability that they test positive is going to be, what is it going to be? 0.74 plus 0.124. And that's going to be equal to 0.198. Okay. So we know that those who had a concussion and tested positive is that. So, in other words, the probability now that they have concussion, given that they were positively tested, is going to be equal to probability that they concussed and were positive divided by the probability that they were positive. So that's going to be 0.074 divided by 0.198. Let's work that out. Divided by 0.198 equals 0.373737. Okay, that is significantly greater than 0.25. So I guess in statistical terms, we would say we reject the hypothesis that probability that they can cast, given they tested positive, equals 0.25. To a high degree of confidence. That we really want to word it formally like that. So now we move on to cricket. The sports census showed 50,000 students, 50,000 students in total. So these ones are changing. 8,880 cricket players, a random sample of 1,000 New Zealand secondary school students found that 120 played cricket. Right? Among secondary school coordinators in New Zealand, it is thought that about 25% of students play cricket. All right. So compare the true probability, the model estimate, and the experimental estimate. The cricket participation in 2023. Discuss which estimate is the most reliable and use statistical reasoning to support your answer. So I guess the closest we've got to the true probability which is, if we had perfect information, would be the 50,000 would be the N equals 50,000 survey. Right, and that says that, so that's, we're going to say the true probability and it's going to be equal to 8,880 divided by 50,000. So the number there seems really, really round, but okay, we'll go with that. Let's work it out. So 880 divided by 50,000 and 0.771776. Declaration of independence here. Okay. Now the random sample probability. So it's not clear whether these are related. The N and it's lowercase n because it's sample is 1,000, and that finds that 120 out of 1,000 play cricket, which is 0.12. Okay, fair enough. Which is different. So there's a difference here. And then the coordinators, what the N sample as unknown, not applicable, and the probability there is to state it as 0.25, which is a lot bigger, which is more than twice sample and about 50% greater than 40% greater than the true probability. So this is the experimental estimate. Okay, so discuss which estimate is the most reliable and why. Now, the most reliable would be the N equals 50,000. Why? Well, the rule of thumb is that the bigger the sample size, the more accurate, the more close to reality. Right? The least reliable would be the coordinates, because either they get this wrong, and if anyone has bias, they're probably, it's going to be them, so that's going to be an unrepresentative sample. We have some worry as well about this random sample. Is it really random? Is this an unreliable? Because it is quite a long way from the 1776. Let's work it out. So it's 32% greater than the true sample, true probability, which is a problem. So most reliable is the first one, 50,000. Least reliable is these cricket coaches, and in the middle there is the random sample, which a random sample. So it doesn't say if these are connected, whether this is being done by a body or as, I mean, this is open to interpretation. This is open to bias. The choice of school would be different. It's not so much these days, I guess, but I would say probably more boys play cricket than girls play cricket. So if this was biased towards all girls' schools or boys' schools, it would be a bit biased, and probably also in a high decile schools tend to play more cricket than other schools. So yeah. All right. School sports census data for ultimate frisbee between 2005 and 2020 is summarised below. So, which year did ultimate frisbee have the highest proportion of the total participants in these two sports? Justify your answer, referring to the graph. It's obviously going to be that one. So it's going to be 2020. So there are actually more frisbee participants than archers. For the first time. I'm not really sure how else you could say that. I think that's the only way you could put it. Next question says, explain why the probabilities created from this data might not correctly represent the probability of a student playing ultimate frisbee compared to other sports in those years. So one thing is the sample is really small. I mean, 1,000 students out of how many? 300,000 something students in the survey. It's quite low. And also, it sort of looks like ultimate frisbee maybe have been either underestimated or be a growing sport, because there is like this huge uptake. I guess we could see an orange here. There is this sort of huge uptake in numbers in ultimate frisbee, which would tend to denote that it's either been underreported or it's a new sport. It's like gaining in popularity really, really quickly. Tends to be, I think at frisbee, I think side will cover some statistics, but it tends to be kind of an informal sport, doesn't it? It's sort of, you can, as long as you have a frisbee, essentially you could play ultimate frisbee. You can use anything as your goal. I've seen them at the university, students playing it, and they play it with a trash can. And so it's a bit of an informal sport. Archery tends to not be a really informal sport. It's one that's really, really expensive to get into to competitive archery. And it is quite organised as opposed to ultimate frisbee. Those two things that I would put. And this next question says sports coordinator is using data from the school to model how long it takes students to decide which sport to play after trying out or rugby and futsal. Futsal was kind of five-a-side, I don't know if it's five-a-side, but it's sort of a scaled down version of five-a-side football with a smaller ball and some skill shots and stuff like that. They're considering using an intervention to reduce the number of students taking a very long time to decide which sport to play. Students who take 4 or more weeks to decide will receive the intervention.
What's going on? Have a seat.
Just imagine what that's like. And the student walks into the room and, everyone from the rugby team is in there. Have a seat, Bill. So, why haven't you chosen which sport? Sounds really over the top. Okay. A bit of a background. It is kind of policy. People are watching this overseas. High school students in New Zealand are encouraged to play at least one sport or both. I know a lot of schools it's compulsory. You have to play an organised sport. And it is pretty much expected that you play a sport. As opposed to other countries that I know where participation is much, much lower. It's really, really a big thing in this country. All right. Now, the table below shows the probability distribution of the random variable x, the number of weeks a student takes to decide which sport to play. Estimate the proportions who will require an intervention. So if they take 4 or more weeks, and here I have kind of accidentally going to need to work it out. 4 or more weeks, so it's going to be that, plus whatever this, plus that. Let's work this out just because we can. So they all have to add up to 1. So grabbing the calculator, 1 minus 0.15 minus 0.1 minus 0.5 minus 0.2 minus 0.18 minus 0.12 minus 0.05 is 0.07. Okay, put those numbers in again, and twice actually, and I got 0.05. I think I made a mistake. Just wanted to make sure because there's a lot of decimal points in there. So 0.05 should be the number that goes in there. So 0.05. Okay. Estimate the proportion of students who will require the intervention. So it's going to be 0.15 plus 0.10 plus 0.05 plus 0.15. 15% of students take more than 7 weeks to decide the sport. All right. So 0.15 plus 0.10 plus 0.05. I'm just paranoid about putting these in properly. 0.45. Which I guess you could say is equal to 45% if you wanted to say it's a proportion. But tricky as these all have to add up to 1. On the home straight, a school sports coach uses observers to classify players from tryouts selected for the squad or not selected. Okay, students who perform the required standards should be selected, and those who perform below the required standards should not be selected. The coach of the goal, the coach has a goal. Coach has a goal of 90% accuracy of selecting the players, correct players based on their ability. So it's not 90% pass, 90% accuracy. Okay, 75 students attended the tryouts. Observer correctly selected 42 out of 50 players who performed the required standard. Okay, so I guess that's 15, and it's going to be 25. Let's go across this. It's going to be 54, and this is going to be 21. So that's the totals who performed at the required standard, but also 12 players from the 25 players who performed below standard. The results of the trials are summarized in the box below, table below. Calculate the probability of students who receive the correct selected or not selected based on their performance. Well, if it's correct, then it's a true positive and a true negative. So it's those two combined. So the portion is going to be 42 plus 13 out of how many students? Well, it's not 100%, it's 75 students. So, okay. 42 plus 13, 55 out of 75. And they're all multiples of 5, so I think this is going to be a nice fraction for us. So 73%. Which is not good enough. He or she was aiming at 90%. Right. Comment on the effectiveness of the observer in selecting the correct players for the netball squad. Support your answer with at least one calculation. Netball. There's no mention of netball up here. It just says a sports team. Okay. Is that a mistake? Well, so presuming that all the numbers above are for netball, then it fails. Because 73% is less than 90%, which is the same name. Which is the state of desired accuracy. Maybe perhaps the observer is better at netball than just sports. It'd be interesting to have a look at the criteria there, whether that's deliberate change from They just mentioned sports coach, and here they mention netball squad. Different wording. Okay. Oh, and that's the end of the exam. All right, fair enough. That's it. Ooh, it was yeah, it was pretty standard. Yeah. I wish they wouldn't have those ones where you fill in the boxes with missing spaces. It does kind of turn it into a Sudoku puzzle rather than a statistics test. But otherwise, yeah, pretty standard exam. Right? Hope you did well.